Swarnov, and our TA is Sabi.
So the problem that we face is that in industrial factory settings, when we try to integrate with new technology such as AI, it's unsafe to train these models around humans in this environment. So what we're going to do is we're going to construct a virtual environment such that our training agent can be trained and could eventually theoretically be placed into a real factory.
So we're part of an existing capstone, but we have taken out the final step, and that's where we work. We're attaching wheels to the cars. So we built our own little simulation to do so.
Yeah, so the scope of our project, while it is for HRI, it doesn't necessarily contain HRI. It contains all the necessary components to eventually incorporate with human-robot interaction.
So here's our project diagram. This is our final simulation that we chose on. We only use one asset for everything as it's simplified, and our goal is to prove that we can build a simulation to include AI for HRI research and not actually prove HRI with multiple people. Here's our integrated project diagram. This is shows where everything is housed. So Unity hosts most of our assets in our game, but we also use ML Agents, which is a library that an extension of Unity for our pick and place training and our interface engine. I also have included our communication diagram to kind of show how stuff talks together because a lot of our assets work and talk together. Finally, this is what we're testing before we move on to each of our main subsystems before we show our final demo. So we care about location, accuracy, and repeatability. This is how we can prove that stuff is working and working correctly over and over again. We are not testing for CPU strain and runtime strain, and as we're not running executables, but actual in-game simulations and tests. We do, though, care that we're not bloating our system with extra runtime tasks. So as long as stuff runs smoothly, that's our main goal for that.
So for my subsystem that I designed is essentially just the construction of the robot arm as well as the reinforcement learning model that runs on top of it. So it has 5 degrees of freedom. Each of these joints needs to be able to be controlled by the reinforcement learning model, and I'll get into the actual model here. So there's 3 main components that you need to understand when doing any type of reinforcement learning model. That's observations, actions, and rewards. For mine, I chose 7 observations to observe the 3 states of the main joint angles, the 3 transform positions that are relevant, and also a phase flag for state transitions. The actions, these are the joints that are controlled in real time at each time step, essentially. And then the reward structure, which is really how the driving force behind training. So there's step penalty to improve time. There's distance to keep it going in the right direction. And success, this is like a lump sum reward that gets applied when it completes the correct task. This is just a visual of the training environment. This is showing nearly after it reaches stability, just it doing the correct task over and over. This is the data associated with that. So this is the primary validation source for my subsystem, where it tails off over there, asymptotes toward the maximum reward. This is just validating that it consistently hit that reward and do the same thing over and over and over again, as well as the standard deviation trailing off to 0. Just briefly on the hyperparameters. So it's using a PPO algorithm. This is just the type of algorithm the neural net uses to train. These are some of the various important hyperparameters. You can think of these as tuning knobs for how to ideally train the model. Yeah.
So I worked on designing our factory and our validation for everything. So on the factory, we have our conveyor belt and our human worker. We decided on making everything as modular as possible. So as more assets get added, we want to be able to quickly change it around using waypoints. We also use a LiDAR that measures distance around the robot, and we also save frame by frame to you'd be able to use for libraries like OpenCV or have it convert to like an RGB depth camera. So our first step of validation is unit testing. So each asset has its own dedicated testing. Each test is run through a virtual simulation. There are no real assets, and everything is recreated the same way every time. So we're able to get almost the same data. Some key ones that we have are LiDAR test, which determine to a fake wall the distance around it, and we can see which points are being raycasted each time. Same thing with our player controllers and our conveyor belt, where we can actually test all of our triggers individually and see what's happening. Secondly, we have system testing. System testing is how we validate everything else. So we have 5 main worlds in which we have individual components in there, or a group of components, seeing how they work together to be able to make sure stuff's happening. We use a lot of console debugging here to make sure that our assets are printing out the right data and they're reading the right stuff. So our first one's our LiDAR test bench. This one, the red lines show our raycasting to our points. So our human is walking towards away from it, and so we can see where it is and what's being there. And our console can actually see the distance are given in phi, rho, and r. So here's a little quick snippet of the actual frames being combined that our row is taking. It is really fast just because we're taking so little frames. So in a short video time, we're losing a lot of data, but you can increase that data to have more use. Secondly, our collision test. This is very crucial for HRI training because when we don't want stuff to collide. So if the robot hits anything, it's bad. And so we wrote some scripts to just say when it touches. So in this example, we use a stick and we ram it into things, and we can see when it collides and what data it collides at. So here's a conveyor belt test. It's pretty simple. This is how we built the conveyor belt to make sure it moves to the right waypoints over and over. As it is kinematically moving, we want to make sure that it is at the right spot and not overshooting or flying and falling. And then lastly, we build an AI list integration. The AI list integration is really useful for being able to make sure all of our triggers work together. We can kind of quickly see if there's something wrong or there's another issue before we have to introduce our AI. So that's being said, that's our subsystem. We'll show you now our full and final demo that runs with our we worked on and built on our final demo. Is there's a couple of camera angles that we can switch to. This is our best looking angle that we have for demoing it, but we can we have one that goes down the conveyor belt line. We can kind of see what's happening there for lining stuff up. And we also can view what the LiDAR sees. Yes. Does take a second sometimes to run, especially with Zoom. Yeah. So here is our project. Moving the red lines are our raycasting spots for our LiDAR. Here's our human walking up. It does kind of go the wrong way sometimes. That's not really a big deal because we are just trying to prove that stuff works and less care about angles. And as long as it's in the rightish spot, our original validation did not require for animations. And so originally just had to stand there.
Yeah, so the main priority is you see that the robot can move and is actually doing all this autonomously. So this is not any sort of pre-planned program. It is choosing to make these decisions based on its training.
So yeah, that's our project. Yeah, cool. Thank you.
Thank you.